Okay, so let's take a look at this sample problem. You're given this teeter-totter, and the length of the whole teeter-totter is 10 meters. That's a very long teeter-totter, but nice simple number. Okay. And you have a father and son, and they're out enjoying their Saturday afternoon. But of course they want to balance it out so it's a little more even-steven. A little bit closer to rotational equilibrium. So if the father weighs 4 times as much as the son, where would you want to put that pivot point? How far to the right of the father, of the 400 Newton force, would you want to put the pivot point? So basically what we're trying to find is the distance from the father to the pivot point. And if I call that x, that's the distance we want to find. So if we were going to set this up, we could write the torque that would pivot the teeter-totter counterclockwise. We want to be equal to the torque that would balance it clockwise, or rotate it clockwise. So on the left-hand side, we know that it's a 400 Newton force, and the perpendicular distance to the pivot point we would just call x. But on the right-hand side, it's going to be 100 newtons. And what should we put in for our expression for the perpendicular distance from the boy? 10 minus x. Like, tell me.
I did D1 plus D2 equals 10, and then I did 400
Oh, that's excellent. That's excellent. Or you can set it up for two equations, two unknowns. So if we solve this now, what does x turn out to be? Well, we're going to have 400x equals 1,000 minus 100x. And then if we add the 100 over, we have 500x equals 1,000. So x equals 2. So this distance right here would be 2 meters. And the distance on the other side would be 10 meters minus 2 meter, which would be 8 meters. Yeah.
There's a relationship between the weight of each person to the distance, right? It stays the same. It's one to four on each person. So could you? Is there a way to figure it out?
Well, no, it's in proportion with the weight. Since one is 100 to 400.
Yeah, no, I'm saying, is there a quicker way to do it since you know that proportion?
You know, if you only have two objects like this, you could just set up a proportion, but you're better off just writing it out this way because we're about to do like more complicated problems where you're going to want to write out the torque formula.
The way I did the first one was like, okay, the small must be 4 times bigger, so 4x plus x.
All right, so let's try one of the more complicated problems. This time the pivot point is put right in the center. And we have the same father-son, so let's say this is 400 newtons. And over here we have 100 newtons. And the plank is 10 meters long. And the pivot point is in the center. Obviously, it's not going to be in rotational equilibrium. Now, we know the distance between the center and the kid here is going to be half the board's length, so that's going to be 5 meters. But this time, instead of moving the pivot point halfway in between the child and the pivot point, we're just going to add some additional weights to make everything even Steven. So right here, halfway in between, so from here to there, that's 2.5 meters. Right there, we're going to add some additional weights. So the question is, of course, how much additional weight would we have to add to balance things out so that there's rotational equilibrium? So when you have more than just two objects, if you wanted to be a little bit more savvy, you could write your rotational equilibrium formula out like this. You could say the sum of all the torques that are taking it counterclockwise equals the sum of all the torques bringing it clockwise. Now on the left-hand side of the equation, there's only one torque, and that's the 400 Newton times the 5 meters. But on the right-hand side, we have the torque from the weights and the torque produced, by the child. So what's an expression for the torque produced by the weights, the additional weight? What's an expression for the torque produced by the additional weight? Just give me an expression.
100 newtons times 5 meters plus 2.5 meters times weight.
I just want the torque from the additional weights. All right, I'm going to call it Fg of the weights times 2.5 meters, yes? Plus the torque from the child, and what's my expression for that? 100 newtons times 5 meters. And now you just solve for the amount of additional weight. Did anyone actually crunch that out?
Explain why we do that.
We both said 600, but it's gotta count for something.
Yeah, you would have gotten a half a point off an hour. Yeah, it's 600 newtons. Because you end up with 1,500 divided by 2.5.
What do you end up with? 1,500 divided by 2.5.
let's look at each individual torque. Like this guy here is pushing down on the board 400 newtons. And how far from the pivot point is that force? Well, it would be this distance right there, yes? And the 400 times that distance, is that going to make the board rotate clockwise or counterclockwise? Right, so that's part of the counterclockwise, yes? And then if we look at the weights, we have this weight right here, but we don't know how much it weighs, so I'm just going to put a little thing right here, say, F sub g, because we don't know what that is. That's our question mark. And how far away from the pivot point is that F sub g? We were told this distance right in here. No, we were told that right in there that that's 2.5 meters. So then we put that expression right in here. Plus the child, the 100 times another 5. Okay? Now an important point is, all of the problems so far, we didn't worry about the mass of the plank. What? All the problems that we've done so far, we've dealt with massless planks, which is like a simplification and idealization, yes?
Yeah, that'd be
So
cool.
we're going to incorporate now the mass and thus the weight of the plank itself.
The pulleys aren't frictionless anymore, and the boards are based on the
So let's take a look at this next problem here. We have this tall building, and on top of this tall building, there's a big construction beam. And this construction beam is not anchored down,
That's dangerous.
it's just set up on top. And some of this beam is actually hanging off the ledge of the building. So it kind of looks like this.
This is so great.
And the mass of this beam is 200 kilograms. Now, again, we'll use relatively easy numbers. Let's let the beam be 10 meters long. And we'll have like 4 meters hanging off the top of the building. So from here to the building right there. 4 meters. Now, unfortunately, the same child from before is
Really?
unattended up on the roof. And this child starts to walk out on the beam. All right, let's make it the dad.
What fell first?
Daddy's doing it on purpose.
question's going to be?
How far can you walk?
How far out can he walk before the beam
I read my physics teacher's
tilts
line.
over? Yes? How far out can he go before the beam's going to be like, oh, it's going to start teetering? You know, what's the breaking point? So we're trying to find this distance here.
So you're gonna set the fuel that it's like that's the max, basically. Find the distance.
So this person right here, they have a weight. How much was that? 400 newtons? So this little distance right in here, that is our x. We're trying to find out how far out can the father walk out on the beam so that the beam is just pivoting. And where's our pivot point this time? Where's the beam going to just start to tilt? Yeah, right there at the edge. Right there. That's our pivot point right there.
The kid at the end.
How high is the building? Is he gonna die if he falls? Who said that he doesn't?
He doesn't go to the limit. He just kind of inches his way out until he starts to feel, and then he oozes his way back. So this time we have to take into consideration the weight of the beam, because it's actually the weight of the beam that's going to be saving this guy's life.
Yeah, this beam weighed nothing.
So if this beam is 200 kilograms, we could do a little side calculation and say, oh, F sub g equals m times g, yes? And F sub g is going to equal 200 kilograms times 10 meters per second squared, which is 2,000 newtons. But some of the beam is going to be actually helping him, holding the beam still. But the part of the beam that's hanging off the ledge, that's not going to be helping him. That's going to be, part of the problem. So what we're going to have to do is break this beam up into two parts. And we're going to have to say, hey, look, we have this part of the beam over here that's going to be providing a counterclockwise torque. And then we have the beam on this side over here. Now I'm going to redraw this diagram a little bit bigger, and I don't like the way I have the man there positioned because it's going to kind of mess up what I need to draw. So I'm going to draw another diagram.
Do we essentially just find 4/10 of 2,000 and not so much weight going against that? Like off the beam? You know what I'm saying? Because it's
I think it's a little bit more complicated than that, but we'll see.
I have no clue what physics is. We'll get to it.
That's it. Guess how? Oh wait, no, that's not what it is.
So, what's the weight of the part of the beam that's on top of the roof, not hanging off? Well, we know the weight of the whole beam is how much?
200. 2,000.
What was it?
2,000 newtons.
2,000 newtons. So we know the weight of the whole beam is 2,000 newtons. Yes?
Yes.
And how much of it, what fraction of it is on top of the building?
6/10 of it.
6/10. So if you take 6/10, because we know that from here to here, is 6 meters, and the whole thing is 10 meters. So we know 6/10 of 2,000 newtons is going to be, what's that going to be? 1,200? So this is the weight of the beam that's on the building. But that weight is distributed over the whole beam. So this gets a little tricky because some of the weight is acting like way over here, which is way far, a big long perpendicular distance from the pivot point. Some of the weight is like right next to it, right there, but that would be a smaller perpendicular distance. And of course, you can do this process all the way on through, and some of the weight is like right next to it, right there, and that weight there is like a very small perpendicular distance from the pivot point. If you were actually going to calculate the torque due to that mass distribution like that, you'd actually need calculus. Because like this little piece of mass over here is exerting more torque than the little mass over to the right.
You can't just find the average.
But in this case, you could just find the average. And this is a big point. This is like the big clutch point of the whole lesson. Okay? Guess where you can let the weight of that segment act? Right in the middle. Okay? We simplify it and we say, hey, look, some of the weight's acting over here, some of the weight's acting over here, but we got this beam that's on the building. Where do we let its weight act? Well, we say right in the middle. So right in the middle, we have its weight. And how much does it weigh, that piece on the building? 1,200 newtons. And what's going to be its perpendicular distance from the pivot point? 3 meters. No, that's 1,200 newtons, because remember, the whole shebang thing was 2,000. This is just the part on the building. Now, the other part that's hanging off the building, this piece out here, how much does it weigh? 800 newtons? Once again, some of it is really close to the pivot point, some of it is very, very far away from it. What's a poor physicist to do? You could say that 800 newtons is acting all right at the center of that segment. So we come up here. And what's going to be that perpendicular distance? So I'm going to make this bigger.
Oh, wow. That's big. Ooh, now I'm really seeing it.
trying to figure out how far out he could safely walk. So what was his weight? Same from the other problem.
400 newtons.
So he was a mere 400 newtons. And we're trying to figure out how far out he could walk. So that's a distance x. Yes? So now we can set up our torque equation.
I thought we know that.
No, x is how far out can the guy walk without tipping the whole thing over. How far out can he go with the beam is just... Yeah, that's why I had to draw a new diagram too. And last time I put the guy halfway out, but maybe it is halfway out, but then I would have a hard time distinguishing between those two vectors. So that's why I redrew the diagram. So now we could say that the torque that's going to hold the beam on, we want to balance it with the torque that's going to flip the beam over. And what's going to be my expression for the torque that's going to keep the beam on? Well, what's an expression for? What do I have to multiply? What do I want to write down first?
FGD.
Which is equal to, what am I going to substitute in?
1200 times 3.
1200 newtons times 3 meters equals
3600. 800 times.
and then the beam that's going to take it over, what's that expression?
800 times 2.
800 newtons times 2 meters. But I have to add the guy's torque because the guy's going to exert a turning force, a torque. And what's the expression for the guy's turning force? The turning force, the torque. 400 newtons times x.
So why do we need to know that it was 2 meters away? Is that just like extreme? No, but it's right there. Oh, okay.
So if you solve for x, now I remember one time I set this problem up and x was like,
500. You get 500.
what does it come out to?
500. Oh, 5.
Oh, so this happened again.
So wait, he has to go beyond the actual plane.
So
He has to go to
what does this mean?
He walks off.
He walks off. Yeah, he can walk to the edge.
Yeah. He's good the whole time.
Unless he walks off the edge.
Unless there was like a massless little piece hanging way out here and he went way out here, okay? But even if he was like right here, he would still be fine.
What if like wind just pushed him over? Like, that's
Well, that would be another story.
a little dangerous.
Wait a minute, did I spell that right? Safely?
Yeah. Yeah.
So do you see, folks? Do you see how we let the weight act at its center? Now, I actually did this a more complicated way because to me it's a little bit more logical if we break the beam up into two parts. Girls, stay with me. This is a punchline here. We broke the beam up into two parts. The part that's on the building and then the part that's hanging off the building. But the truth of the matter is, We could have let the weight of the whole beam act at the center of the whole beam.
Okay, that makes sense.
But bam! We didn't need to break the beam up into two parts. I think it's more like logical to look at it that way, but let's just go back and do the problem over a second time quickly, yes? You got the building. Okay, you got the beam. You got the guy. Here's the pivot point.
You're doing it so small again.
But it's not a problem now.
Which one's easier, you think?
So, what was the weight of the whole beam?
2,000.
2,000 newtons. Where can I let the weight of the whole beam act?
5 meters.
In the center of the whole beam, which would be like right there, yes? And it's 2,000 newtons. And from there to there, that would be 5 meters. But we wouldn't be interested in that. What's the perpendicular distance from that weight force to the pivot point? 1 meter. And how do we know that this right there is 1 meter? Well, we know the whole thing is 10 meters, and there was 4 meters hanging off the ledge. So we can let the whole 2,000 newtons act at the center of the beam, which would be 1 meter away from the pivot point. And then we have that guy out here. His weight is 400 newtons. And we're trying to figure out how far out can he walk, x. So now we say, hey, the torque that holds the beam back, if it was equal to the torque that carries him over, how far out can he walk? Well, what's going to be the expression for the torque that holds him back?
The 1 meter plus times
2,000, careful. What's the perpendicular distance from that 2,000 Newton force in the pivot point?
1 Newton, right?
1 meter. And what's going to be expression over here?
His weight.
400 newtons.
So would you just want to do it this way? Isn't it easier to do it this way?
Yes. And what does x turn out to be? 5 meters.
Six on the thing, the middle, the pieces that are shaped side to side, so 6 times side is 1. So then 2,000 times 1
That was
equals
like
400 times x.
way quicker.
Equals 5. I'll get that on test.
This is what you want to do from now on.
Yeah, I think we're gonna do that.
But we kind of just proved to ourselves that this does work. Okay, so that's how you handle the weight of the beam.